So in this video, we can look at how we can represent the motion of objects on a velocity time graph. We can look at how we can calculate the acceleration using the tangent to the curve of a velocity time graph. And finally, we can look at how we can calculate the distance travelled under a curved time graph by looking at a technique for working out the area under curves on a velocity time graph. So we're now going to have a look at how we can represent the motion of a vehicle using velocity against time. And first of all, again, we've got to think about what the significance of the gradient is. Well, of course, the gradient is the change in velocity over the time taken, which is acceleration. So if we've got a straight line, that means we've got a constant acceleration. And of course, we need to work out the acceleration itself. So acceleration is the change in speed over time. The change in speed is 60. The time taken is 10. So that gives us 6 meters per second squared. Every second, the speed changes by 6 meters per second. Just be careful with this line that's flat. Loads of people say it's stationary, but look at the axis. This says velocity, so it is carrying on at a constant speed of 60 meters per second. The next one, of course, is constant acceleration again, but it's a lower acceleration, so the rate at which the speed increases is less. And again, the acceleration here is changing speed over time taken. The change in speed is going to be 20, and the time taken is going to be 10, so that is 2 meters per second every second. Look at the difference in gradient, it's a third what it was there. And the final line, that's a constant deceleration because you're slowing down. And you use the same equation to work out deceleration, the change in velocity over time, and that's 80 divided by 10, which is 8 meters per second squared. Notice it is the steepest of any of the gradients. If you are asked to work out the acceleration, well then the acceleration is going to be minus 8 meters per second squared, because every second you're taking away 8 meters a second. And that one there at the bottom is when you are actually stationary on the axis, the x-axis, when your velocity is 0. So what else does a velocity time graph tell you? Well, let's have a look at this area under the straight bit here. We're travelling at 60 meters a second, and the time that we're travelling for is 20 seconds. Now, of course, distance is speed times time. Well, the speed is 60 and the time is 20, and that makes 1,200 meters. You'll notice that that is also the area under that line, because it's 60 times 20, which is 1,200 meters. So the area under a velocity time graph is the distance travelled. So the area under the first part here will be a half times 60 times 10, half base times height, and that will give you 300 meters. And the end, we've got another triangle. The area is a half times the base, which is 20, times the height, which is 60, and that gives you 600 meters. So of course you can then work out the total distance travelled, 300 plus 1,200 plus 600, and that gives you 2,100 meters. So I want you to pause the video now and have a go at this question. I want you to describe the motion of each section. You can call that A, B, C, and section D. And where appropriate, include values. So I want to know if it's constant speed, what value, if it's accelerating or decelerating, what is the value. And finally, calculate the total distance travelled in the journey. So pause the video, have a go at that, and I'll go through the answers in a minute. So in section A, it's travelling with a constant acceleration. And that's equal to the change in velocity over time. Notice I'm writing the equation out first, which is 40 divided by 10, which gives you 4 meters per second squared. On part B, you're travelling at a constant speed. Give a value, it's 40 meters per second. C, again, you're travelling with a constant acceleration. Again, acceleration is change in velocity over time, and the change in velocity is 20, and the time taken is 10. So that's going to give you 2 meters per second squared. And finally, this is a constant deceleration. Again, we use the same equation. Acceleration is change in velocity over time. Deceleration is the same. The change in velocity is 60, and the time taken is 20. And that gives you 3 meters per second squared. So part B, you want to find the total distance travelled. Well, we can split this up into a triangle, a rectangle. You could do a trapezium, or you could do another rectangle and a triangle and a final triangle. So the first one is the area under this triangle is a half base times height. So that's going to be a half times 40 times 10, and that's 200. So that's 200. This you can see is base times height, which is 40 times 10, which is 400. This is the same size, 400. That's 20 and 10, so that's a half base times height, so that would be 100. And the final one here, you've got a half of 60 times 20. So that's 1,200 divided by 2 is 600. So adding all the distances together, we get 1,700 meters. And I'll definitely show on your diagram where you're calculating each part. So now I want to look at interpreting the curved graph again. So of course this time we've got change in velocity over time, and we know the gradient is acceleration. So you can see that you've got an increasing gradient, so you've got an increasing acceleration. So you can say the acceleration is increasing, so the rate of change of velocity is increasing. That's the amount of velocity is changing every second is increasing. And of course the curve's the other way, then the gradient is decreasing, which means the acceleration is decreasing and the rate of change of velocity per second is getting less. So what I would like you to do in a second is to pause this video and have a go at this question here. But before you do that, I want to bring your attention to the following. Lots of students, when they're given a graph, do not first of all make sure they know the scale on the x and y axis. So if we take the y-axis first, in 2 we've got 2 divided by 5 squares. So 2 divided by 5 is 0.4. So that each square is 0.4. And on the x-axis we've got 1 divided by 5, so each square is worth 0.2. Make sure that you think about that and write that down on axes or next to axes before you do a question. So pause the video and have a go. So it says calculate the acceleration between points P and Q. So that's the gradient of the graph. So acceleration is change in velocity over time, and you need to really show you're working. The change in velocity is your final velocity, which is 8, minus your initial velocity, which is here at P, which is 0.4, 0.8, 1.2. Divided by the change in time, the time taken, well, the final time was 3.8, minus the time you started, which was 1.24. And that gives you 2.8 meters per second squared. The next part says calculate the distance travelled between points Q and R. So first of all, that is the area under the graph, and you can see that that is the rectangle bit there. So it is the area which is going to equal 8 times 5.2 minus 3.8. So that's the difference there. You could just work that out on your calculator first and then multiply the two together. I'm doing it this way, so I show the examiner exactly what I've done. And that gives you 11.2 meters and not meters per second, as I wrote in my pre-recording. Sorry. The next thing, describe the motion of the car between points R and S. Well, you can see the gradient is changing and it's getting less steep, so the acceleration is decreasing. Be really careful with things like acceleration is slowing down, because you're trying to link acceleration and that sounds like you're thinking about the speed. So be really careful. The acceleration is decreasing is what you need to be saying there. And finally, calculate the acceleration at 6.5 seconds. And we know acceleration is the gradient, and at this point we have a curve. So remember, the first thing you do is to do a right angle to the curve at that point, and that's 6.5. You then draw another line which is at right angles to that, and that is now the tangent to the curve at that point. So now I've got to work out the gradient of this graph. And so to save time, I'm going to make sure that where I can, I choose whole line. So you can see I'm going to choose this line here, going down, and therefore I'm going to use that triangle there. So acceleration is the change in velocity over time. My change in velocity in the time from 3 to where it crosses here, which is going to be 7.7. So in the time between 3 seconds and 7.7 seconds, the velocity is changed by 10.48. That's 11.2. That's 11.6. So halfway will be 11.4. And the time taken was 7.7 minus 3, because that's the time taken. So that is your gradient, and that gives you 6.7 meters per second squared. Now, of course, it depends on your drawing of that gradient, and so there'll be a range of values that you could get within in order to get the result. So finally, the last few things I'm going to do with you. First of all, how do you estimate the distance travelled when it's a curve? Now, I know at Maths GCSE you use trapeziums to do this. In the science syllabus, it clearly states that you have to estimate it by counting up squares. And so we're not use these tiny squares, we can use these big squares here. So first of all, if you imagine, we're going to work out what the area of one big square equals in terms of distance travelled. So the area of one square in terms of the distance travelled will be 2 times 1. So that signifies, so that represents 2 meters. And then you count up the number of squares. So the number of squares is equal to, well, that's 1, 2 roughly. I reckon that and that, because it's only up to R, so I reckon that and that between is 3. Then I've got, well, that's 4. If you think about that going to there, so I reckon that's about 4.5 altogether. Might be slightly over, but you are only estimating. So I'm going to make it 4.5 squares altogether. So you can see what I've done. I've just roughly estimated that area. So the total distance is going to be the number of squares times by the distance represented by each square. So I reckon that's about 9 meters. And of course, again, because it's an estimate, there'll be a range of values in the exam that you need to get between. It might say between 7 and 11. As long as you get within there, you get the marks. But you're showing the process of how you've done it. So pause the video and have a go at this question, which asks you to estimate the distance travelled along a section of railway journey in figure 2. So it's the whole of that area. So of course, first of all, you're going to work out the distance for the distance travelled in 1 square. So 1 square, the distance is equivalent to 5 times 100. So that's 5 times 100. So each square represents 500 meters. And then 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's about 9 with those. 10, 11, 12, 13, 14, 15. That, and that is about 16. I reckon that and that is about 17. So it's about 17 squares in all. You could, if you want to dot the other ones. Oh, we didn't do that one. So I reckon I forgot to include that one. So I reckon that's about 17 and a half. So 17 and a half squares. So the total area equals 500 times 17.5, and I make that roughly 8,750 meters. And again, you would have a range of results. You can get 1 mark for that, you can get 1 mark for counting the squares, and 1 mark for that as long as it's within a reasonably accurate range.